Замечательно.
Ну, вы
Так, вот у
меня,
нас
когда
на нашем
объявите, то я
семинаре.
начну. Виден ли мой экран? Скажите,
Да,
пожалуйста.
значит, на нашем, давайте я сначала
Видно.
вас представлю. Вот, ну, сегодня на нашем семинаре мы открываем второй семестр нашего семинара, кафедрального семинара кафедры общих проблем управления. Сегодня у нас докладчик Василий Олегович Мантуров. Я правильно указал вашу аффилиацию, да, физтех, вот.
Естественно.
Потому что за последние годы у вас были разные аффилиации, и
Ну,
заграничные, и
Да.
наши
чего?
отечественные.
Ну, семинар у меня начался.
Вот, тихо, тихо.
Потом.
У кого включен микрофон? Пожалуйста, выключите. Так, значит,
Ничего.
вот.
Ну, вот
Сейчас я
начать, говорят,
вы-
включи микрофон,
выключу
пожалуйста.
микрофон. Вот так.
А,
Так,
м, а, да.
все, пожалуйста.
Yes, да, я очень благодарен. I'm very grateful to the organizers of the seminar for having me here. And I'm going to speak in English, if you don't mind. And today I'm going to talk about a very general method how to solve equations. Well, I think I will have nothing with differential equations, especially with
Я что-то не понял, мы что, на
algebraic.
английском языке будем вести,
Здравствуйте.
да?
Да, у нас очень много
Well,
иностранцев сегодня.
yes,
А,
yeah, so
понятно.
so yes, well, I will mostly speak about some equations which appear in topology and which originate from physics, but I will mostly concentrate on something called the pentagon equation, and here is the outline of my talk. First, I will talk about the general essence of the photography method, what this is good to, what this is good for. Then I will tell how to guess the solutions of equations, how to look at some geometry, and by looking at length or angles or some other objects, areas, we can easily guess some solutions. And then we can check it algebraically, and then it will give us some. So I think that any solution to a nice equation gives an invariant of something. And for me, it's good because it's about braids and maybe knots and maybe manifolds. So those equations I will mention, they really appear in topology, and actually they are related to many ubiquitous things. I think they are themselves ubiquitous. And for example, it's very popular now to talk about cluster algebras. I will mention them a little bit. The goal is to give a way of finding invariants of some topological objects, and actually not only topological, but maybe some other. And so what is usually a topological object, or maybe algebraic object? So usually we have some representative. So for a manifold, it can be a triangulation. For a knot, it can be knot diagram. And even for a group, for a group, we can have mm, uh, generators and relators. So we may have a word in some alphabet. And those words are or triangulations or diagrams are up to some moves. And we want to get an invariant out for those moves. And the equations I'm going to solve will not be even written because they can be written in many forms. And actually, today I will talk mostly about one equation, the pentagon equation. And I will be solving them by using some common sense. То есть я буду решать уравнения в каком-то смысле из соображений здравого смысла и угадывать решения. Well, and actually here I want to give some citation of Confucius, 心有诗, 理有理, 诚有乐. So, нужно быть вдохновленным поэзией, а дальше утвердиться в ритуале и прийти к совершенству посредством музыки. Вот я сегодня приведу пример, как мы можем угадать решение алгебраически, а дальше, извиняюсь, угадать как раз геометрически. Дальше доказать его алгебраически, а дальше, уже имея формулу, можно играть в разные игры, ну, например, логика или там формальная алгебра, там конечные поля, все что угодно. То есть вот сейчас я этот пример продемонстрирую. На самом деле вот этот метод фотографии, я его начал в 3-м году, и с тех пор был некий список публикаций, они указаны в архиве, на самом деле сейчас их уже больше. И вот список некоторых моих соавторов. Ну, пожалуй, самые главные мои соавторы — это Кауфман, ну а также вот мой ученик Ким Сон Джон, Игорь Никонов, Иван Джиян. Ну, на самом деле, когда я об этом думал, я разговаривал и с Клиффордом Хенри Таубсом, и с Виктором Матвеевичем Бухштабером, и с Владимиром Георгиевичем Тураевым, и с Сергеем Владимировичем Фоминым, с очень многими людьми, которые занимаются разными науками. И вот когда я разговаривал с Бухштабером и показывал ему некоторые соотношения, ну, например, то же самое соотношение Пентагона, которое только-только вот появится скоро, он мне сказал такую вещь. So I will switch into English. So when I was talking to Victor Buchstaber, and told him about the Pentagon equation I'm going to solve, and said, well, it's related to cluster algebras, it's related to braids, it's related to manifolds, it's related to other things. He said, well, you see, so people speak different languages, and somehow here is a language of geometry, here is a language of differential equations, here is a language of algebra, and very often people talk about the same thing. And if we see that the same picture appears in different sciences, it can be known under different names. And if so, once people understand that they are speaking about this one and the same way, some knowledge from one science give rise to a breakthrough in another area. Actually, the Pentagon equation was first well known for getting invariance of three manifolds, but then I understood that it can be used for getting invariance of braids. But it was just the very beginning in 2023. So in 3 years, I understood many more connections. Okay. So the photography method is like this. Roughly speaking, we have several states. What do I mean, a state? Well, I mean that we have some representation of our object. So, for example, we can have a manifold, and a manifold can have a triangulation. We can have a word in some group, and well, an element of a group, and this group can have a word. And for this state, I want to draw write some data. Usually I will say draw, not write, because I prefer to draw equations, not to write them. And so there is some data. So if I want to construct an invariant, I should get some formula from my state. For a manifold, I have to take a formula for a triangulation, for example, and out of some data. And I want to have it invariant under some moves. You see, I want to find a rule formula when I switch from one position to another position. And well, sometimes when you see some book on topology and people want to introduce you into some theory of invariance, for example, of knots or manifolds, they start giving lots of pages of definitions. Here is a category, here is a monoidal category, here is a braided category, and a lot in the sense of Bourbaki. So several pages of definitions and then just an example. So usually people talk about category. I will talk about in terms of pictures, and I will draw pictures. And my data will not be very restricted. I will talk about some edge length or angles or something like that. Okay, so the main keyword I will be using during my talk is Ptolemy yields pentagon. So there is a well-defined Ptolemy relation, yes, that if we have an inscribed quadrilateral, then AC plus BD equals XY. The product of diagonal length is equal to sum of two products of edge length, of opposite edge length. And this can be thought of as a transformation. So if we have this ABX and CDX, this is a triangulation of the quadrilateral. And if I switch from X to Y, I get another triangulation of the quadrilateral, and this is Y. And here, I prefer to write this Y as AC plus BD over X. So this is the Ptolemy transformation rule for me. And now I will tell what it means Ptolemy yields pentagon and why it is good. AC plus BD over X. What is it is good for? Okay. So I will be drawing equations. Well, you see, why don't I write equations but draw them? Because in topology, there are famous examples. I can tell, well, Young-Baxter equations, or Zamolodchikov equation, tetrahedron equation, and many others. So if people like tensors, they write the Young-Baxter in this way. If people like matrices, they may write this way. If people like group generators, they may write this way. Somehow you can take tensor product, somehow you can take direct sum, somehow you can take a group. But in essence, this is about the same. Of course, categories will be very, very different. And but I prefer not to write equations, but draw equations. And now the warming up example, which is the main example, and I want to consider it completely. So what do I mean by the pentagon equation, уравнение пятиугольника? Well, it is known that there is one triangulation of a triangle, is the triangle itself, if I don't allow any interior points. It is known that there are two triangulations of the quadrilateral, like this and like that. And this is number 2. And it is known that there are 5 triangulations of the pentagon. They are drawn here. And you may see that for the hexagon, there will be 14. And for the heptagon, there will be 42. And probably you may guess that these are Catalan numbers. And actually, not only we can count the number of triangulations, but in fact, these numbers are just the numbers of vertices of some polytope. This is called the associahedron. It's a very beautiful polytope, or it is also called Stashev polytope, and it was first suggested by James Stashev for topology, but then it turned out that this polytope is very useful in various sciences. For example, it's related to Conway freezes. It's related to associators, bracket structures. It's related to cluster algebras and many other sciences. Probably I will draw a flower of this. Okay, and now the pentagon. The pentagon, what does it mean that the Ptolemy yields pentagon? Let me put some data here on this triangulation of a pentagon. By some data, I mean I put edge length A, B, C, D, E and X, Y. A, B, C, D, E, 5 edge length and 2 diagonal length. X, Y. And then there is a data transformation rule. The data transformation rule for me is when I change my triangulation, and for the new triangulation, I get a new data according to the prescribed rule. Well, in the very beginning, I said that this fact that Ptolemy yields pentagon is not mine, it's a common knowledge. But after the photography method, you will see that I will get many other solutions to the pentagon for free. Okay, now you use this transformation rule that you put instead of X, you put something like Z, which is maybe AY plus BE over X. So I perform the Ptolemy transformation for this quadrilateral. In some sense, if you ask what are variables and what I want, I would say that instead of variables, I say that I want to put some data here, and I'm looking for a data transformation rule such that after I return back after 5 steps, I get the same data. What do I mean by data? I can put some labels on edges. I can put some labels on inside triangles. I can put some labels for angles. I can do something mixed. And so my question is, what data can I take so that after 5 transformation, I return to the same data? And I will get some answers. And actually, almost all answers I get will be can be guessed for free from some geometry, and then they can be proved by algebra, and then they can be generalized. So this is what I'm going to talk about. Okay, есть ли вопросы какие-нибудь? Are there any questions? Okay, so far so good. By data here I can mean edge length or angles or areas, and I want to do triangle flips and data transformation rule. And actually, this fact that Ptolemy yields pentagon is a very popular topic in cluster algebras. And these polytopes and for the quadrilateral, this is a segment. For the pentagon, it's a pentagon. For the hexagon, the set of triangulations, there are 14 of them, is encoded by a trivalent graph, by a three-dimensional polytope, which is called the Stashev polytope, and you can read a lot about this beautiful construction of triangulations of polytopes in the book by Gelfand, Kapranov, and Zelevinsky. And actually, they are considered from topological, categorical, and many other points of view. And we were considering that from the point of view of group theory. So you see, many areas of mathematics are related to this Ptolemy-Yields pentagon. And actually, some years ago, I saw a beautiful paper by Félixson called Ptolemy Relation and Friends, and somehow Ptolemy relations and cluster algebras are ubiquitous. They appear everywhere, and there is a cluster algebra flower where we see to which areas of mathematics and physics they are related. Just here I put well, actually, I want to say that from this flower there is a lot of petals of this flower which are related to the photography method. So actually, I will encircle. So these are parts of mathematics related to the photography method. Okay, and now I'm about to start proving the photography method. So here are petals related to the photography method. So you see cluster algebras, quivers, triangulations of surfaces and manifolds, Stashev polytopes, tropical geometry, invariance in low-dimensional topology, and also some theorems from school. You see, there are Desargues theorems and other theorems about points and lines, configurations of points and lines, which mostly give rise to some equations like pentagon or octagon. I can say what an octagon relation is. And since they fit into some picture, this picture allows one to say that we get invariance of many objects in topology, for example. And actually here we may say about clusterization, patternization, tropicalization, and so on. What do I mean by that? Well, actually, if we have invariance of our object we want to construct, then we can say, okay, since they are related to cluster algebras, we may dream about constructing invariance from cluster algebras. We may dream about getting invariance coming from tropical geometry. As for tropical geometry, you will see it in today's lecture. Some of those programs are already realized, and some others are in the process. So actually, I have students, I will mention them, working in the photography method, and I will be happy to share problems with further colleagues if there are any interests. Well, now I can talk a little bit about invariance of braids. Well, maybe I can now, yes, okay. Allow me to show the proof of the main statement that the Ptolemy yields pentagon. Okay, here it is. So here I have five edges of the pentagon and two diagonals of that. When I perform a flip here, instead of Y, I get Z. And Z is like this. Okay, I perform another flip, and instead of X, I get T. And T is like this. And when I substitute Z, I get this. And I do it 5 times. And after a careful calculation, I return to this position, and I see that the final edge lengths are exactly X and Y as they were before. So this is a formal proof. And as Arnold was usually saying, I know how to prove it, but I don't understand it. So this is somehow a formal algebraic proof. But I want to tell you a proof without anything. By the way, now I want to say something with a small gap. Я специально сейчас допущу некоторый пробел в своем доказательстве. Вот. Но я сейчас хочу немножко помахать руками и сказать, I want to have some hand waving and prove the statement without writing anything. So how can I prove this without writing any formulas?
Можно вопрос?
Actually,
Вот перед тем, как мы пошли дальше, вот в чем состоит утверждение? Доказательство, например, я понял, а утверждается что?
утверждается, что если мы поставим некоторые данные на ребрах и
Да.
сделаем 5 раз вот это преобразование, то мы вернемся к тем же самым данным, то есть x и y.
Но у нас, получается, диагонали тоже каким-то образом, да, обозначены буквами. То есть у нас есть 5 сторон, 5 диагоналей,
Да.
и мы делаем соотношение между, скажем, там, 3 сторонами или 4 сторонами и 2 диагоналями, и после этого эти соотношения применяем несколько раз. Или неправильно?
Да, именно.
Угу. Так,
Ага.
а как формально можно, как это можно вообще сформулировать?
Сформулировать это можно так. Мы задаем данные на каждой триангуляции. Под данные я имею в виду букву на ребре триангуляции.
Да.
И, значит, есть данные и есть правило преобразования данных. Вот правило преобразования такое, что в результате нескольких преобразований мы возвращаемся к тем же данным.
То есть можно сказать, что у нас даны длины сторон, да, и
Да.
вот а длины диагонали, они как бы не даны, но они, допустим, обозначаются параметрами. И
Да.
тогда вот у нас одно и то же соотношение, его, значит, как бы 5-я степень дает тождественное, да? Из этой картинки.
Да, вот. Okay, so and actually there is a proof. You may find it speculative, but the proof can be like that. Well, actually, if you have a pentagon, then and put this data here, then from this data you know the other diagonals, the other 3 diagonals once forever. So this data defines everything. And actually, if you start from here, for example, from T and Z, you will get here, and you will get to prescribed X and Y from T and Z once forever. There is some formula, you may even not know it, but it will work. And if you go this way, never mind, you will get to the same X and Y. So this is the main argument, that if you have some data, you can restore any other data at once and uniquely. Well, actually, there is a gap in this proof. Maybe you have seen this gap. If not, I will say the gap is that this happens provided that all those quadrilaterals are inscribed. So actually, I haven't yet proved completely that Ptolemy yields pentagon.
Can I interrupt you again? Excuse me, because this is the matter of understanding. Yes, so I think this is important. Yeah, my argument is the following. Of course, if we are given with 5 length of a pentagon,
yes,
and if we know that this pentagon is inscribed, then we actually know everything. So
yes.
X and Y are not quite arbitrary in this case.
Right, and this is a gap. This is a gap in the proof. Well, actually, this
is a big gap, I would say.
Yes, this is a big gap. Yes, actually, I have the proof of this fact without calculation and without a gap. And actually, this proof uses something called lambda length. But I prefer to share the proof with gaps. And lambda length is something like logarithms of reduced length of an ideal pentagon in the Lobachevsky geometry. I'm not going to tell in the details, but there is a beautiful proof. Actually, there is a beautiful proof that Ptolemy appears somewhere else. And Ptolemy appears somewhere else. This means the following. If we have an ideal quadrilateral, we want to look at edge length of these edges. Of course, this is the absolute, and edge length are infinite, but we can cut them by some circles. No, I think we should cut them not by circle, but by horospheres. And if we cut, then the remaining edge length will, if I flip a diagonal, if we take their logarithms, they will satisfy the same pentagon. Well, it can look a bit complicated, but in this setup, there is no gap because edge length can be because these the lambda length can be more or less arbitrary. So they need not be inscribed. So we need not use the condition for them to be inscribed. However, here I want to mention some other things which are also very important, that even if I believe that here everything works, initially A, B, C, D, X, and so on are a length. So they are positive integers. And moreover, initially, there are some, for example, triangle inequalities. But finally, I get some relations for formal variables. And then I will generalize it by means of algebra and logic. And now I will see how. You will see how. So you see, if I have some length, and I know that they satisfy triangle inequalities, I can say, okay, I have some equation between rational functions, or finally equation between polynomials, which is satisfied provided that some inequalities hold. But if some polynomials are equal, provided that some inequalities hold, then it means that some equality holds in a large subset of the space, so it holds everywhere because they are polynomials. Okay, and so if it holds everywhere, this means that it holds for formal variables. And if they hold for formal variables, we can completely forget that these are length. So we start from geometry, and then we know that algebra will give us a proof. And once we get a proof, we can forget about geometry. And this is a very important fact. Also, I want to mention one more thing concerning these cluster algebras. But concerning this relation, there are so-called cluster algebras. I'm not going to give a definition of this. And these are very beautiful algebras introduced by Sergei Fomin and Andrei Zelevinsky about 25 maybe years ago in relation to representation theory, and they are related to lots of parts of mathematics and physics. And in particular, there is some positivity principle and some Laurent phenomenon, meaning the following, meaning that if we do these transformations, as I did here, actually in the language of cluster algebra, it is related to something called seed mutation, if someone knows. Then after this transformation, what we get will be always low-rank polynomials with positive coefficients in the numerator. Let's look. So here I have z is xd plus ce over y. Then I, instead of, I substitute something here, and I get a more complicated expression here in the right part. And actually, I have to divide something by, I have to make some division. I have to divide something by a polynomial. But surprisingly, everything will be canceled. В итоге останется многочлен Лорана. It will be a Laurent polynomial. So at each step, what I have in the denominator will be cannot be a polynomial. It can be a monomial only. So you see everywhere I have a monomial in the denominator. And also another surprise which I can take from cluster algebras is that in the numerator, I have a, what do I have? I have only positive coefficients. I take a sum, not I don't have minus sign. So only plus, not minus. And now I will give you one more surprise, which is called the tropical geometry. Actually, there are semifields, and there is a beautiful, there is some beautiful part of mathematics called tropical mathematics, which is used, which was initially used in algebraic geometry for counting some curves and other things by replacing some initial equations by something called tropical equations. So what is a tropical semifield? So first of all, a semifield means that we have multiplication, we have division, and we have addition. And no subtraction, no. And the most popular example is when A star B is just A plus B, so I can put it in quotes, or sometimes people encircle this product, so A star B in quotes is A plus B. A divided by B in quotes, as you may guess, it's A minus B. And as A plus B in quotes, it is maximum of A and B. In some sense, some people like maximum, some people like minimum, but both work. Actually, by a semifield, we mean the structure with these operations with usual laws, commutativity, associativity, and distributivity, but no minus. Okay. So this is the tropical semifield, and here is a statement. Tropical Ptolemy also yields pentagon. So what is a tropical Ptolemy? I should take A times C tropically, plus, here tropical plus, B times D tropically, and with I tropical divided by X. What does it mean? When I multiply, this means plus. Here again, plus. Divided by X means minus. And this plus means maximum. So this is X to Y, which is like this. I wrote work in progress, but this is already and this is a paper by my student Gurnor Singh. Well, he proved it, and then he proved that it gives an invariant of braids. I will tell you about braids a bit later, but now I want to collect examples. So why does the tropical Ptolemy work? Why does the tropical Ptolemy satisfy the pentagon? Here you see we have some transformations which give rise to x and y. So what does it mean? It means that we have an equation. This equation is in rational numerators and denominators. It will be an equation in polynomials. So we see that one polynomial in A, B, C, D, E, X, Y is equal to another polynomial. And you see during the process, I never use minus sign. And if I never use minus sign, then actually this should work in any semi-field. I use only plus, multiplied, and divided. And the only thing I use is distributivity, commutativity, and associativity. So then it should work in the semi-field, hence it works in the tropical semi-field. And of course, you can make an exercise and this will prove. So you see, I started from geometry. I guessed a solution by using geometry. Then I used algebra to prove it formally, and then just logically, I can get two variables, and sometimes I can get to generalizations like tropical generalization. In the first example, as Vladimir Yurievich mentioned, if I don't use lambda length, buckles, and a large gap, saying that without calculations, the proof was only modulo some inscribedness relation, if I don't use some other geometrical consideration. But now let's do another thing. Well, assume I have a quadrilateral which is not inscribed, A, B, C, D, E. And I can take one diagonal E and the other one F. And then there is a formula which expresses F in terms of A, B, C, D, like this. Well, I'm pretty sure that not many people remember this formula by heart. And even I do not remember it because it has huge square roots. This formula, well, many people were finding different forms of this formula, but anyway, there are square roots. And it's quite hard to work with. Even if I run it into the computer, it would be, so computer algebra is not working very easy with applying this formula 5 times. And actually, even in today, in 21st century, this formula for the second diagonal is published in journals like American Mathematical Monthly. So this is a tricky formula, F. I don't remember it, but now I formulate a theorem that if we apply this formula 5 times to the triangulation of the pentagon, then after 5 transformations, I get to the initial label. So this is the way of how to solve equations without writing them. And you see now the proof is obvious by just hand waving, because here, if I have this formula, then starting from 5 length and 2 diagonals, I know the other 3 diagonals once forever. And here I need not make any restrictions to inscribedness. Okay? This formula is hard. Do you want more? Okay. So if I live in not in the plane, but if I live in the sphere of radius 1 or with curvature 1, then I have another formula, f prime, another formula for the other diagonal of the pentagon. And again, the same theorem. If I apply it 5 times to triangulations of the pentagon, I return to the initial labels. The same for the hyperbolic Lobachevsky space. Again, I have a formula. Well, actually, in this formula, you can find it on the web. There are not only squares, but sines and cosines. And here you have squares, hyperbolic sines, and hyperbolic cosines. These formulas are huge. But again, both work and give solutions to the pentagon. So you see, I know how to solve equations without writing them, and even without writing the solutions. I solve them. And now more and more and more examples how to solve the pentagon. Later on, I will talk about something called octagon, maybe. But now I want to say, why only length? I said the word data. So you see, by data, I can mean whatever I want. Maybe by data, I mean something written on edges. Maybe by data, I mean something written inside triangles. Maybe by data, I mean something rolled for angles. And again, now assume I have a pentagon. Then, for example, I can take its angles. Angles of the triangle. And if I have these angles of the triangle, for example, Euclidean triangle, well, actually, I can play the same game in the hyperbolic geometry of some curvature, for example. But I assume I have some angles of the triangle. Then, after I make such a flip, I can rewrite these angles of the triangle by using the sine rule and the cosine rule. Просто по теореме косинусов я могу вычислить все углы. По теореме синусов и по теореме косинусов. And then, well, if I have angles, then my polygons, quadrilaterals and pentagons are restored uniquely up to similarity, с точностью до подобия. Well, in the hyperbolic case, they can be restored completely, but in the Euclidean case, up to similarity. And again, if by data I mean measures of angles, and I use these solutions with the data transformation rule coming from the sine rule and cosine rule, after 5 transformation, I return to the initial position, okay? Well, so at least now you see that there are lots of examples. Well, actually, there are some things called shear coordinates, which appear in cluster algebra theory, and there are more transformations, and again, they satisfy the pentagon. Well, again, by geometrical reasons. So I can guess many things. And now you may ask, what does it have to do with braids? Why do I get invariance of braids, invariante cos? So the idea is as follows. So what is a braid? Usually when talking about a braid, I'm drawing several strands, нити, которые находятся в трехмерном пространстве. So when I have several strands, which do not intersect each other. So I get something like this. So this is a typical picture of a braid. But this braid can be also considered as a dynamical system. So we have n points on the top and points on the bottom, and we have some dynamics. Points move on planes in some time. So points are moving, and something happens. And for topologists, an invariant of braids are invariants up to isotropy. So I can perturb a braid continuously without making any intersections. And by perturbing this braid continuously, I want to have an invariant. So if I move my braid somehow, I want to have the same invariant. But what do I mean by an invariant of braid? Actually, braids form a group, and group can act on something. So I want to put some data on the top, and there will be some data transformation on the bottom. So I want to have some rule for transforming the data from the top to the bottom. Excuse me, there is some problem with seeing. Do people see the picture?
Ну, у меня видно, по крайней мере.
Okay. So I want to have some data transformation so that for isotopic braids, I have the same. Okay, and now how can I get this data? Actually, there are very beautiful pictures called Delaunay triangulations and Voronoi diagrams in honor of Boris Nikolaevich Delaunay and Georgy Feodosevich Voronoi. So the idea is as follows. Assume we have points on the plane. Then I can split the plane, tile the plane into regions. So actually, I want to draw the world map so that I have capitals in these points, and my state, my country, consists of points which are closer to its capital than to any other capital. And generically, if my points are in generic position, then we will have a trivalent graph. So if we draw a world map, then generically there are no three countries, no four countries having common border. So usually there can be three countries having a common border point, but not four. And generically. And this is a picture. This is a typical picture. So I have points here, dots, and these are countries, okay? And here is the Delaunay triangulation. By edges, I connect neighboring countries, okay? These are neighbors. And now assume my points move. Why do points move? Because I want to draw a braid. So points are moving in time. I have a braid. And as they move, I can do some transformations. Which transformations can I do? For example, I can put some labels on edges. And after I perform some moves, I should get some transformation of labels. And I want this transformation given by a braid to be invariant in the sense that for isotopic braids it is the same. And now I want to say why pentagon is important here. Actually, the pentagon is important because of the following. So assume I have 5 points, 5 points which are almost on the same circle, almost. Well, actually, why does such a flip happen? Well, you see, when I draw this plane tiling, so I have circumscribed circles because here I want to understand which region is closer to this point or that point. And the change of the combinatorics changes exactly at the moment when 4 neighboring points are on the same circle. At this moment, we have this. And if I perturb it in different directions, I get a flip. So my combinatorics changes exactly when 4 points are on the same circle. So before I have that, after I have that. And this is a Voronoi diagram. And as for Delaunay triangulation, it's the dual graph. So the Delaunay triangulation was like this, and it will become this. So, and now I want to ask, what should the data transformation rule be if I want my transformation to be invariant, an invariant of braids? An invariant of braids means for isotopic braids, it gives the same answer. And actually, now there is one easy observations that braids form a group. And if we want to check that something behaves good for braids, we should check the trivial braid. So if we want to prove that the action is well defined, we should check that it's trivial for the trivial braid. And now I will give you the most important move for the trivial braid. And the most important move is as follows. Assume we have 5 points which are almost on the same circle. Almost. And of course, there will be some Delaunay triangulation for these points. I don't know, maybe this. And this is almost an inscribed pentagon, right? And now I want to move these points a little bit. So I can move these points a little bit so that at some moments, some 4 points are on the same circle. And what will happen with this triangulation? Well, it can undergo flips. So it can undergo one flip or another flip, or maybe it will undergo all 5 flips that I drew before. But the braid here will certainly be trivial because I move these points a very little bit. They are just in some small neighborhoods. There is no actual braiding. There is no such move of one strand around the other. So this is a trivial braid. And you see, the relations I have to check is the pentagon relation. Well, I showed you why it is necessary to check the pentagon relation, and actually it is sufficient to check the pentagon relation plus something which happens obviously. I don't have time to say why, but the main thing we have to check is the pentagon relation. So this means that all things I mentioned before, Ptolemy, tropical Ptolemy, and whatever else gives invariance of braids. Also, it is known that it gives invariance of 3 manifolds. Also, it is known that, well, many other things, because this equation appears in physics. And it appears in physics, comes from physics and appears in topology. And now you may imagine whatever favorite picture you like. For example, you can say, okay, let's take an octahedron and let's take a triangulation of this bitetrahedra and look at some, I don't know, edge length again. For example, maybe not octahedron, but better to say, okay, yeah, maybe octahedron, okay? We can take an octahedron and split it into tetrahedra and, excuse my quality of drawing. So let it be an octahedron, and we can split it into tetrahedra and put some data on edge length. And what about flips? Well, flips correspond to bipyramid, something like that. So if we have two tetrahedra which share a face, and then we can so this is a way of splitting the bipyramid into two tetrahedra, and there is a way of splitting it into three tetrahedra like this. So you connect opposite points, and then you have and then you can split it into three tetrahedra. And again, I would say that there is a rule of data transformation rule when you can express this edge length in terms of existing edge length, and they will satisfy some equation. I will not tell exactly which equation I have, but you can imagine that it is related to some transformation for polytopes, and this corresponds to something coming from physics and working in topology. By the way, here is some calculation corresponding to a non-trivial braid. So for the trivial braid, the answer is trivial, and for a non-trivial braid, when I have 5 points, like 3 vertices of the triangle, the midpoint on the triangle, and 1 point moving around the center of the triangle, I will have a sequence of 6 transformation, which gives rise to something very much non-trivial. So this is how to calculate examples of my invariants. So the tropical case, the case with spherical and hyperbolic spaces, not only length, but also angles, and also what other data can be here. Well, actually, I'm not going to talk about de Graaf-Witten invariants. It will be too much just for one talk, but I can say that by data, I can mean whatever I want. So in the initial picture, for a triangulation, I took edge length, A, B, C, D, E, X, okay? And I looked at some geometry. I said, okay, if I have, say, a pentagon, and if I put edge length, then, for example, five edges from plus 2 diagonals allow me to restore everything. But here, for example, instead of length, I can say, okay, here I have A, B, and for example, I can put some group elements. I can use some group theory, group G, and put some group element on an edge. And group elements, for example, if I have 3 group elements A, B, C, then there is some cycle condition A, B, C equals 1 in the group, and so on. So I can use some group theory. And again, I can use some правила здравого смысла. I can use some proper sense rules saying that I can restore one picture from another. And then I can get to invariance, and actually this is how one can describe something called de Graaf-Witten invariance. There are invariants of 3 manifold called de Graaf-Witten invariance, and then so there is such a formula. Well, I'm not going to talk about this formula, but it's rather complicated. It uses some groups, some cycles and cocycles, but actually the essence of this formula, as I understood, is the photography principle. When I put some elements of the group on edges, for example. Also, well, we can play this game, and I think people can still play. So what about just sets? Maybe, I don't know, and I think it's puzzling. Maybe we can put some sets in vertices and edges or something like that. And maybe there is a natural rule to restore the sets in a good way, so that for the pentagon we have from this picture you can restore any other picture once forever. Maybe we can use set theory. I don't know how, but if we can do it, we will have some set theoretic solutions to the pentagon, and then set theoretic invariance of braids. I don't know how to do it, but I hope it can be done. So you see, there is a lot of possibilities. Actually, you see that data can be put not only on edges, it can be put on angles, or actually, one more solution to the pentagon used areas, and I was putting some data inside triangles. And actually, this was a solution to the pentagon used by Korepanoff. He was using some labels inside triangles like ABC, and after performing a flip, his idea was that here we use, well, instead of A and B, you use, say, P and Q. And A and B were some variables, and P and Q were some something which was linearly linearly expressed in terms of A and B. It was a sort of matrix, and he was looking for such a matrix which would give me a solution to the pentagon. Again, I was looking at areas, and geometry give me a hint how to get his solutions. So for the pentagon, I looked at many different ways, and they all got to invariance of braids, for example. Well, actually, here is the three-dimensional case, and here what I have is so-called Pachner moves, and this is useful for getting invariance of higher manifolds. Well, I can just say what Pachner moves are. These are some very fundamental moves for transforming one triangulation of triangulatable manifold to another. So, for example, if we have a two surface, we can triangulate it by triangles. And so if you want have one triangulation and another triangulation, then combinatorially, we can get from one to the other by using two moves. One is called 2-2 move. This is our flip that we saw before. This is 2-2 move. And the other one is called 1-3 move, is when you have a when you have a triangle and you put a point inside. So this is combinatorially, so this is 1-3 move and 3-1. And combinatorially from any triangulation here, you can get to any triangulation there by using these moves, 2-2, 1-3, and 3-1. And you can easily imagine that in higher dimension, there are also sets of moves. For example, for dimension 3, there are moves 2-3, 3-2, 1-4, and 4-1. And so this means that you can that in any dimension you have a set of moves. You can write down sets of equations, and you can use the pentagon relation to guess how solutions to these equations may look like. Well, I don't know. I want to talk about this in detail. Actually, cocycle is volume. There are Crane-Yetter equations similar to Seiberg-Witten. Yes. Well, actually, for higher dimensions, I can use some other principle, but now I'd prefer to stop the substantial part of the talk and just advertise what's going next, and to have more time for questions and comments. Well, okay, of course, I can talk about manifolds of higher dimensions, and I can manipulate, for example, for volumes of triangles or tetrahedra, and say that, for example, there is one more trick how to prove that some equations work. The tricks can be like that. So if I have a bipyramid and I can split it into two tetrahedra, like this and that, then I can have a volume. Well, of course, there is a formula for the volume of a tetrahedron in terms of its edge length. Okay, there is a formula for the volume. It's hard, but it exists. And then if I have such a bipyramid, its volume is equal to the sum of two volumes. On the other hand, I can split it into this. And if I split it like into three tetrahedra, then I will have a formula that sum of two will be equal to the sum of three. And then you can manipulate with formulas and say, okay, I have a solution to the equation that the sum of two is equal to the sum of three. And that is good for getting invariance of some other topological objects. Okay, yeah, so this is what I was talking about. Okay, this is again a toy. Yeah. Yes, I'm not talking about any concrete formulas. Yeah, okay, so actually this means that if I use Kelly-Menger for the tetrahedron, I would say that somehow Kelly-Menger will satisfy some six-term move, six-term relation. Again, the proof is like Ptolemy satisfies pentagon. Well, here are some references. Actually, what we started from, and actually we started from some observation that pentagon appears in two different branches of low-dimensional topology. That something that people used for manifolds can be used for braids. We were inspired by that, and we understood that it can be used for further. I gave a diploma work for Rohoshkin. So, for example, I took some solution to the pentagon from the black box from another science, and I immediately got an invariant of braids. This was a diploma work of my student. And here is some list of students, and not only students, but colleagues. And actually the first one who was using the word photography method was a Chinese mathematician Wang Jian. By the way, my co-author Wang Jian is also a co-author of Yao Shentong, of the famous Yao. He is writing papers, topological papers with Yao. Actually, with Igor Nikonov, we were relating braid invariants in many various ways. Actually, oh, excuse me, not S. Kaufman, Lou Kaufman. With Kaufman, Kim, and everywhere S. With Kaufman, Nikonov, and St. John, I was talking about working about invariants of manifolds. With Rohoshkin, I was working about braids, Delaunay triangulations, and so on. Actually, this list is incomplete. There are many other people now working in the photography method, and some further research directions. Again, not complete. So first of all, cluster algebras. By that, I mean that instead of just data, which is very simple, like edge length or angles or areas, I can put something more complicated with some more complicated structure, like cluster algebras. And I see there are pentagons everywhere, and I can use cluster variables or flips, something called seed mutation and so on. again, we had a whole flower of cluster algebras. We saw that cluster algebras are related to this and that and that. So from those parts of mathematics, we can take examples and relate them to invariants of braids or maybe manifolds, and maybe we can do the opposite. So for example, there is something called Conway-Koster-Fries patterns, which are related to number theory. There are associators. Associators are very nice thing related to non-associative multiplication. So if we have a triangulation of a polygon, it is known that the number of such triangulation is equal to a Catalan number. And if I fix a point here, then I can encode triangulations by bracket structures. And the number of bracket structures corresponds to a Catalan number, and actually different brackets. So we can get flips of brackets like ABC goes to ABC, and these flips correspond to triangle flips. So we can imagine that for some non-associative structures, we can again get solutions to the pentagon equation. And actually, some years ago, maybe in the end of 20th century, it was very popular to talk about categorification, which means that instead of just usual invariants like numbers or polynomials or some other easy things, we wanted to construct an invariant valued in something substantial, having some category, and now I expect that we can look for tropicalization, clusterization, Friesification, whatever you see in this flower of cluster algebras, for example. Yes, and also there is a nice task of extracting solutions to the pentagon equation from braid invariants. Actually, somehow if we have an interaction between two parts of mathematics, like pentagon and braids, then we can, and we know that there is a relation in one direction. From a solution to the pentagon, we can get a braid invariant. We can ask the question, can we get a solution to the pentagon equation from any braid invariant? It's like if we have some algebra helping topology, can we expect that topology helps algebra? Sometimes it does, and it's a challenging problem. So now you see there is a lot of problems here, and also there is a lot of computational problems, because somewhere we have invariants and we know how to calculate them. Somewhere we have invariants which are hard to calculate. For example, if we use formulas with square roots and sines and cosines, and we have to use computer algebra. Okay, and actually, now I want to advertise that we are running several projects where we have Telegram channels and so on. For example, we have seminar friendship. So today's seminar, which is joint, is some partial case, and we have friendship with many seminars, and we advertise talks between each other. And sometimes we read mathematical papers together, which means that if I want to read a paper from some part of mathematics, and I know that there are specialists knowing it better than me, I can share it. And also there are mathematical circles, математические кружки, friendship, and actually many other projects we have with my students. And thank you very much for the attention.
Okay, thanks very much for the interesting talk. So please, questions. Пожалуйста, вопросы. Ну, если пока
Yeah,
все
I would be
думают,
happy to have
давайте.
some keywords. So, for example, if you have some keywords from the list, I don't know, whatever, and say, okay, this keyword, I don't know, algebra or pentagon or group or whatever, is somehow related to any part of your research, just name this keyword. I would be happy for that because just recently I used DeepSeek program. It's a completely artificial intelligence problem, and I can say, okay, just tell me how cluster algebras are related to representations of objects of such a type. And it suggests me dozens of articles where something may be related. So maybe if you say something, we would see that some some parts of mathematical sciences can potentially be related. I would be very happy to have some keywords which could be in common.
Okay, I understand, but probably we are not ready yet, but we can think of it. Just maybe maybe I turn to Russian. Maybe it would be better for most of our listeners. Вот ну, как бы у меня есть несколько вопросов, но, к сожалению, времени, они предполагают очень длинное такое обсуждение. Я, может быть, потом уже задам в частном порядке. У меня такой общий вопрос. Вот, значит, во-первых, здесь, ну, давайте так. Ну, вот в духе того, что вы упомянули, скажем, кружков, да, ну вот кружки математические. Вот. Ну, есть целые темы, так называемая геометрическая интерпретация, когда мы решаем систему уравнений, а потом вот если мы выясним, что параметры, входящие переменные, имеют геометрический смысл, то у нас сразу получается решение из геометрических соображений. В чем, собственно, здесь ключевая разница с методом фотографии? Вот я пытаюсь здесь понять, в чем то, что называется novelty.
Novelty в том, что очень часто, м, а, очень часто любая картинка с геометрическими данными есть уравнение. И любое решение уравнения есть инвариант чего-нибудь. Вот, например, есть теорема Дизарга и есть так называемый флип Дизарга. И оказывается, что этот флип Дизарга дает представление группы кос, потому что он решает из геометрических соображений. То есть уравнения, которые я решаю, они в основном происходят они в основном нужны для топологии и как правило, происходит из физики. Но на самом деле, когда я говорю, что есть так сказать, из общих соображений, то это не всегда из общих геометрических соображений. Я, например, могу использовать теорию групп. То есть я специально везде, где только можно, избегаю слова категория, потому что если я говорю слово категория, например, я говорю матрица, тензорное произведение, я очень сильно себя обедняю, я себя загоняю в рамки. А когда я говорю данные, дата, то я, наоборот, могу делать что угодно и как угодно. И вот, например, поигрался с геометрией, потом перешел на группы. Вот хочу перейти на множество. Так что вот не только, значит, геометрические соображения, и геометрические соображения, как видно, бывают разные, ну, хоть евклидовые, хоть гиперболические, ну, какие угодно, в принципе. Вот это, ну, и на самом деле некоторые из моих коллег говорят, что, в принципе, метод фотографий мог бы в некоторых задачах заменять теорию категорий, потому что данные — это гораздо более широкие, дают гораздо более широкие возможности, чем какие-то там тензоры или там матрицы или что-то, что математики где-то используют.
Да, спасибо. А вот число 5, оно почему здесь такое ключевое? Вот
Опять сейчас я
есть
скажу.
очень много, да, очень много
Сейчас я
работ по
скажу.
поводу тоже
На самом деле,
диструктивирования. Почему
на
именно
самом
оно?
деле тут так. На самом деле тут так. В размерности 2 симплекс имеет 3 вершины. И здесь, значит, преобразование, оно отвечает многоугольнику, у которого на одну вершину больше, то есть это флип четырехугольника, а соотношение отвечает многоугольнику, у которого на две вершины больше. Это пятиугольник. В разменности 4, в разменности 3, извиняюсь, там, значит, исходным объектом является тетраэдр, а преобразование это бипирамида с 5 вершинами, а соотношение это октаэдр с 6 вершинами. Вот. А на самом деле есть еще у меня октагон, восьмиугольник, по другим причинам. Он тоже связан с методом фотографии, но просто сегодня я не успел поговорить обо всем вообще. Вот, то есть октагон тоже можно решить, уравнение восьмиугольника, оно другое, но оно тоже решается из геометрических соображений и тоже дает разные инварианты для топологии. Вот так.
Спасибо. Так, пожалуйста, еще вопросы?
У меня вот еще такой простой совсем вопрос. Метод фотографии. Почему вы вообще используете это, так сказать, понятие?
Да, вот, so there was a question, why do I call it the photographer method? So the idea was that I take a photo of my object. So for example, I look at a three manifold. I want to take a photo of this three manifold. I can look from one position or I can look from another position. And actually, I want to have some data from this position to restore the whole picture. So maybe some of my colleagues are talking that it may be good for image recognition or something like that. I want to have an invariant of my object by looking at some position of photo. For me, one position is one triangulation, another position is another triangulation. So this was the source of my of this name. And actually, I want to have invariants which are which are more significant than just numbers or polynomials, and which come from making photos in different from different perspectives. So this is what my name originated from.
То есть вы фотографируете с разных сторон, а потом, значит, это объединяется
Да,
в одну
а
картинку.
потом вот преобразую данные.
То, что, да, то, что как бы в старшем поколении называлось начертательная геометрия во всех технических.
Да, я люблю начертательную геометрию. Вот я говорю, теорема Дизарга, она, вот, вы знаете, so you see, when I showed my photography method to, сейчас, well, I will answer, there was a question on the chat. When I showed my photography method to Clifford Henry Taubes, Clifford Henry Taubes is a great mathematician who found that there are continuously many smooth structures on R4. In dimension 4, this is the only dimension when there are smooth structures which are not diffeomorphic to each other. Well, and he found, yeah, and when I showed my picture to Clifford Henry Taubes, he said, oh, okay, there is some similar picture in the paper by Fomin and Pilявsky. Well, actually, he just said, okay, I see something similar. I see a similar picture. I looked at the paper by Fomin and Pilявsky, and I immediately understood that the Desargues equation, the Desargues theorem gives an invariant of braid groups. So I want to emphasize, as Buchstaber told me at some point, that if we see similar pictures in various areas of mathematics, you should try to see that one area of mathematics can give solutions to problems in the other. Если вместо пирамиды взять три призму, well, I think the prism is not the elementary object. It's like 4-dimension 2, your initial object is simplex, and then you should have quadrilateral for data transformation and pentagon for data relation. It's like this. So somehow for triangulations, there is one triangulation of the triangle, which is a point. There are two triangulations of the quadrilateral, which can be somehow correspond to an segment, and there are 5 triangulations of the pentagon which correspond to a pentagon. And in dimension 3, you have a Stashev polytope or a sociahedron. And yeah, hyperplanes, yes, actually, configurations of planes and points, something is done and something still to be done, but the number of my problems is much larger than the number of students I can work with. So yes, some problems are formulated in my papers about the Desargues theorem and generalization. For example, octagon appears to configurations of planes, for example.
Thanks very much. So unfortunately, we don't have time for further discussions because I believe that there are I believe that this talk could inspire discussions which might be long and might be quite
I would be
informative.
very happy to proceed
Yes,
answering this
there are
question.
many new things there, and they should be thought of. Okay, thank you. So,
If you have the recording, please send it to me. I would be happy.
yeah, sure. Yeah. And so I think, well, maybe I turn to Russian. Ну, такое, в общем, у нас такое сегодня достойное начало, я думаю, нашего семестра. Есть над чем подумать. Спасибо большое докладчикам.
Спасибо вам огромное за
Спасибо
приглашение.
слушателям.
Я очень рад выступить. Да.
И до встречи через неделю. Да, до
Спасибо.
свидания.
Все хорошо.